Chapter 10, Numerical Methods. Chapter 10 is dealing with a couple of methods of finding solutions to equations that you otherwise would not be able to solve using the standard algebraic methods you've learned so far. So in order to first of all understand what we're doing, we are finding solutions to an equation which is of the form f of x equals 0. So we are trying to find roots of that equation. So first of all, the function needs to be continuous on the interval a to b, and in the if the value of f of a and f of b have opposite signs, then this means that the root exists between a and b, at least one root. It could be more than one. So as long as there's a change of sign between the value of function at a and the value of function at b, then we can be certain that the root exists. Now, the continuous function, it simply means that there is no asymptote that is defined for all values between a and b. That means it's like a nice, continuous, smooth curve. For example, here, if you've got a function which is a cubic, it's sketched here, and in this example, we have to show that there is a root between the values of 2 and x equals 2 and x equals 3. So that means the root, very often we call that root alpha. So let the root be alpha. Then we can be certain that alpha belongs to the interval between 2 and 3. If I use the square brackets, that means including endpoints 2 and 3, but you can also use curly brackets 2, 3. That means that the endpoints do not belong. This is the same as saying alpha is between 2 and 3, inclusive of 2 and 3, or alpha is between 2 and 3. So that's just an explaining you the notation that I've been using, that I'm going to be using. So over here we've got to show that there is indeed the root between 2 and 3. You could see on the sketch that the graph crosses between 2 and 3. So that's what we can do. We can find the value of the function at 2 and the value of the function at 3, and you will see the change of sign. So it's going to be 2 cubed minus 4 times 2 squared plus 3 times 2 plus 1, and this one here is 3 cubed minus 4 times 3 squared plus 3 times 3 plus 1. So if we substitute 2 into the function, the way I like to do it, if I have to use that several times, I can just use the ans key. So put 2 first and do ans cubed minus 4 ans squared plus 3 ans plus 1. So that gives me the value of minus 1. If I put 3 in, so put 3 equals, scroll up to find the rule, and the answer over here is 1. So you could see that the function changed sign. This is less than 0, this is greater than 0. So there is a root exists. So you could also, you need to learn two comments. So a change of sign, continuous function is something you could add as well. Therefore root exists. Well, should add it to your explanation. Now if you notice, if you want to test f of minus 1 as well, so if you put minus 1 equals, let's scroll up, put it there, you'll get the value of negative 7. And then if we just consider the interval between -1 and 3, then you can see that the change of sign also is there. Okay, so the root exists. In the interval. But as you could see that there is not one but 3 roots between those two values. Okay, so that confirms that there is at least one root exists. If you look, okay, so this is actually part B of example 1. We are asked to show that f of x has a root between 1.4 and 1.5. So the idea is here to substitute 1.4 into the function. So evaluate what 1.4 is, what value it gives you, substitute it in and write down the answer as well, and state whether it's positive or negative, which can be done using inequality symbols, and then do the same with 1.5. So you don't need to necessarily show that you're substituting both cases fully, but I think it's a good idea to do it at least once. So at 1.4, this is going to be 0.104, which is clearly greater than 0. I could say it's positive. At 1.5, this is minus 0.125, which gives you a negative answer. So this shows that the curve crosses the x-axis between the values of x at 1.4 and 1.5. If you imagine part of the curve looks like that somewhere there, because it's, oh, actually the other way around, sorry. Let's just do it in red, because 1.4 is positive and 1.5 is negative. So something like this is happening. So what you need to do, you don't need to obviously draw the graph, you just need to say f of x is continuous and there's sign change, therefore the root is in the interval 1.4 to 1.5. There you go. Okay. So in the example 2, we've got a function given 54x cubed minus 225x squared plus 309x minus 140. And it's a cubic function, and we are provided with a sketch. We are told that this happens between 1 and 2, that big wobble. This is your y-axis and that's the x-axis. And we're told that there is a student who observed that f of 1.1 is definitely a negative, and so is the value of function of this function at 1.6. And therefore he concludes that there is no roots between 1.1 and 1.6 because there's no change of sign. Now, if you look at the diagram, that's clearly not the case. 1.1 and 1.6, they are both negative, so maybe 1.1 somewhere here, 1.6 somewhere here. You could see both values are definitely negative, but you could see that there could be 2 roots as the graph crosses the x-axis twice between those 2 values. So from the graph, we conclude that there are 2 roots between 1.1 and 1.6 as it crosses the x-axis twice. Now, if you look at part B, it asks us to find the value of the function at 1.3. So if that's 1.1, somewhere here, 1.3, maybe it's positive. Let's find out what the value is. So it's a good idea to actually show that you are substituting 1.3 into the equation. There you go. And then evaluate it. There you go. So we are going to put 1.3. I've already got the function in here. So that gives me the value of 0.088, which is positive. And then if we find the value of 1.5, as they ask us, so if we put 1.5, substitute it into the equation, and you get minus 0.5, which is less than 0. And we are asked to explain why there are at least 3 roots on the interval between 1.1 and 1.7. So 1.1, we've tested, that's negative. So if you look at that, we've got 1.1, that gives me negative answer. 1.3, somewhere here, that's positive. So you can see there's a change of sign. So there's at least 1 root between these values. And you've got 1.5, and that is negative. So there is a change of sign here. So the graph has to cross the x-axis at least once. And then at 1.6, we also have a negative answer. So what I need to do is check what happens at 1.7, as the question refers to 1.7. So over here between 1.5, without looking at the graph, you could have a function just staying below the x-axis or popping up and down, but it's a cubic, so it will, at maximum times, it will intersect the x-axis 3 times. But let's just put 1.7. Let's just sub it in. Oh, I think I've lost it. Just put it in quickly. 54 ounce to the power of 3 minus 225 ounce squared plus 309 ounce, and then minus 140. That gives me the value of 0.352, which is positive. So you could see that the graph will have to cross, we don't know whether between, well, we do know between 1.6 and 1.5, because there's only 3 points of intersection if it's a cubic at its maximum. Right, so how do we explain it? So we need to say that there's a change of sign between 1.1 and 1.3, so one root as change of sign. Could be more, but because we know that there's another root, so another root, again change of sign, and the function is continued, and the third root as there is sign change or change of sign. So we definitely know no more roots, so that's how we confirm it. Okay, so let's have a look at example 3. That was example 2. Okay, I'll just check where is my. Okay, so in the example 3, we have got we've got to sketch on the same axis the graph of ln x and y equals 1 over x. So let's have a look at this one. So you need to be confident you can sketch the function y equals ln x without any problems. Okay, so ln x, it goes through 1 on the x-axis, and it's a increasing function. It goes up to infinity, so it's defined for x is greater than 0, and the range is all real values. Okay, now we also been asked to draw y equals 1 over x. So the intersect here, there's a graph here, there's the other branch, and it's not defined for x is equal to 0 as it's an asymptote. However, it says explain how the diagram shows that there's only one root, so you could say clearly the graphs intersect at one point only. So there is only one solution to the equation ln x equals 1 over x. And it says explain how that shows that there's only one solution to the equation, or one root to this equation. So this has one root only, as if you could see, as f of x equals 0 is the solution to the equation ln x minus 1 over x equals 0, which is the same as the solution to this equation. There you go. So the same solution as f of x equals 0, but we've already said that ln x equals 1 over x has only one solution, which we deducted from looking at the graph. And now to show that the root lies, that's for part B, in the interval 1.7 and from 1.7 to 1.8, we need to find the value of the function at 1.7. Our function is the function that we are finding the roots of, so this is our f of x. So we've got to find ln of 1.7 minus 1 over 1.7. So let's just put ln ans minus 1 ln won't work. Let's just put 1.7 in 1.7 in. Try again. Ln ans, close brackets, now it should work, minus 1 over ans. Okay, so that's minus 0.057, so it's clearly negative. Let's find the value of the one function at 1.8. 1.8 equals, scroll up, that gives me the value of 0.0322. That's greater there. So function is continuous and sign change, therefore root exists. Now for part C, we are told that the root is alpha. That's what I said to you before. Very commonly we call it alpha. And we show that the root is actually, this is a very important question, show that alpha equals to 1.763 correct to 3 decimal places. So the way we're going to show this is just this idea of looking at the values either side of 1.763. So imagine if you are going to consider all the numbers that round down and up to 1.763 will be the ones that are, if imagine this is 1.764, this is 1.762, all the values starting from the lower limit up to the higher limit. Okay, technically speaking, this here will round up if you consider 1.7635, but we are using the bounds in this method. There you go. So we're going to go half of that amount between these two values and these two, and that's what we are going to test. We are going to substitute these two lower and upper bounds into the function f of x and show that the graph must pass between those two values, therefore it rounds to 1.763. So you could test values closer to 1.763, so you could have gone and substituted 1.7629 and 1.7636 if you wanted to, but that's quite a nice and comfortable way of doing it, just looking at the bounds. So the function that we are substituting this in is our ln x minus 1 over x, because that's the one that we are solving when it's equal to 0. So I've already got it typed into the calculator. Okay, so let's substitute it in. That gives me, you can see how tiny this number is. It's minus 6.4 times 10 to the power minus 4. So it's clearly negative. So for the value 2.5, that's negative. And for the 1.7635, if I substitute this one in, that will give me a positive value, 2.4 something times 10 to the power of minus 4. So that's clearly positive. So you could see that you could visualize the graph passing somewhere between these two values. So maybe here, maybe there, maybe bang on in there. So anything in any value between these two bounds will round to 1.763. So I need to state that there is this function is continuous, so f of x is continuous, and there is sign change. Therefore, root is correct to 3 decimal places, because here we are not proving the existence of it, we are proving that it is correct to 3 decimal places and it's equal to 1.763. So you can have a go at the exercise that follows this example, which is exercise 10A.